Humanity has always been captivated by the moon, but serious scientific exploration only began in the 1950s with the development of robotic spacecraft by the United States and the Soviet Union. The first probe to reach the moon was the Soviet Luna 1 mission in 1959, which flew past its surface. This was followed by Luna 9 in 1966, achieving the first successful soft landing. 3 years later, Apollo 11 made history when American astronauts became the first humans to set foot on the lunar surface in 1969. In the decades since, many nations have launched orbiters and landers, and as of January 2024, 5 countries have successfully landed spacecraft on the moon. Despite these remarkable milestones, one region of the moon long remained unexplored, its far side. This hemisphere never faces Earth, making it permanently hidden from our direct view and earning the misleading nickname the dark side of the moon. In reality, sunlight reaches it just as often as the near side. It is simply turned away from us. Visiting it requires traveling there by spacecraft. Today, advanced observatories like the James Webb Space Telescope allow us to study regions beyond the lunar horizon, opening a new era of discovery. As we explore the moon's hidden hemisphere, we uncover lesser-known features and long-standing mysteries. Whether people see shapes resembling faces, animals, or symbols on the moon's surface, everyone on Earth is observing the same hemisphere. So why is the far side never visible? The answer lies in the moon's relationship with Earth. The moon takes almost exactly the same amount of time to rotate once on its axis as it does to orbit our planet. As a result, the same side always faces Earth. This phenomenon is known as tidal locking, a spin-orbit synchronization that keeps one lunar hemisphere permanently turned toward us. The moon does have a true dark side, but it is not fixed. Which regions are shadowed depends entirely on the moon's phase. During a new moon, the side facing Earth is dark because the moon lies between Earth and the sun. At full moon, the near side is fully illuminated while the far side is in darkness. Over time, every part of the moon experiences both sunlight and shadow. The far side remained unknown until 1959, when the Soviet spacecraft Luna 3 delivered humanity's first images of it during the early years of the space race. By modern standards, Luna 3 was extremely primitive, yet Soviet engineers managed to send it into lunar orbit just 2 years after Sputnik 1. The spacecraft captured 29 photographs using photographic film, remarkably, film originally designed for American spy balloons due to its radiation resistance. These images were developed, fixed, and dried on board, then scanned and transmitted back to Earth using a crude mechanical system. Luna 3 carried 2 cameras, one wide-angle and one narrower with higher resolution. Although only 17 images were successfully transmitted, and just 6 were clear enough for publication, they revealed roughly 70% of the moon's far side and completely transformed lunar science. One striking difference became immediately obvious. The far side lacks the dark basalt plains, or maria, that dominate the near side and form the familiar man-in-the-moon pattern. These maria were created billions of years ago by ancient volcanic eruptions. Instead, the far side is heavily cratered, featuring impact scars so vast they span distances comparable to small countries. During the Cold War, the Soviet Union began naming newly discovered features, a move that sparked international debate. Among the most dramatic discoveries was the immense Mare Orientale impact basin, visible only near the moon's edge during favorable librations. Although first identified in 1906 by Julius Franz, Luna 3 revealed its true scale, a massive, bullseye-shaped structure formed by an asteroid roughly 64 kilometers wide nearly 4 billion years ago. Measuring more than 900 kilometers across, the crater rivals the length of the United Kingdom. Later volcanic activity partially filled the basin with lava, creating one of the few maria on the far side. In 1965, the Soviet mission Zond 3 expanded upon this work. Equipped with a much improved camera and capable of scientific measurements such as spectroscopy, Zond 3 returned 23 high-resolution images that helped produce one of the first detailed maps of the entire lunar surface. At the same time, NASA was advancing rapidly toward human exploration. President John F. Kennedy had committed the United States to landing astronauts on the moon and returning them safely before the decade's end. In December 1968, Apollo 8 carried Frank Borman, Jim Lovell, and Bill Anders on humanity's first journey beyond low Earth orbit. They became the first humans to witness the moon's far side firsthand. Lovell described it as a gray, colorless landscape resembling plaster or beach sand, densely covered with rounded craters, many formed by meteorite impacts. Apollo 8 passed behind the moon. Communication with Earth was lost for about 10 minutes. This blackout terrified both the astronauts and mission control in Houston. Apollo 8 had ventured farther than any human mission before, completely cut off from Earth. When the signal was finally restored, relief swept through the control room. Charlie Duke later recalled how dramatic lunar sunrise was. Unlike Earth, where dawn gradually brightens the sky, sunlight on the moon appears instantly, casting long, sharp shadows. He described the far side as extremely rugged terrain and remarked that he would not have wanted to attempt a landing there. 2 months before Apollo 11's historic landing, NASA launched Apollo 10 in May 1969. Crewed by Gene Cernan, John Young, and Tom Stafford, the mission served as a full rehearsal for a lunar landing, testing the lunar module in low lunar orbit, following the success of Apollo 8. While circling the moon's far side, however, the Apollo 10 astronauts experienced something unexpected, an incident that would later fuel conspiracy theories and prompt NASA to clarify the facts decades later. While passing behind the moon, the crew heard strange sounds over their radio system. These noises puzzled the astronauts at the time, though they were later explained as harmless interference between the spacecraft's radio systems, technology that was advanced for the 1960s but primitive by modern standards. Apollo spacecraft were notoriously noisy environments, filled with the constant hum of fans, engines, and mechanical vibrations, along with the occasional loud bang or thump. Still, the sounds heard during Apollo 10 stood out. The astronauts described the noise as resembling a whistling or warbling tone, similar to the eerie sound produced by a theremin, an electronic instrument often used in 1950s and 1960s science fiction films, as well as famously featured in the Beach Boys song Good Vibrations. Though later analysis confirmed the sounds had no mysterious origin, recordings of the event have been repeatedly misinterpreted in modern conspiracy media, despite the explanation having been publicly known since the 1970s. As lunar landings began in earnest, a familiar mission pattern emerged. 2 astronauts would descend to the surface while a third remained alone in the command module, orbiting the moon. These solo missions, carried out by Michael Collins, Apollo 11, Dick Gordon, Apollo 12, Stuart Roosa, Apollo 14, Al Worden, Apollo 15, Ken Mattingly, Apollo 16, and Ron Evans, Apollo 17, are often considered among the most psychologically demanding feats in human spaceflight. While alone, these astronauts mapped the moon's surface, photographing terrain no human had ever seen before, and conducting meticulous observations over several days. Al Worden, who orbited the moon alone during Apollo 15, frequently described this experience as one of the most profound of his life. He recalled that views from the far side, when both Earth and Sun were hidden, were unlike anything imaginable. The stars appeared in overwhelming numbers, forming what he described as a vast white sheet, each point of light representing a distant sun. One question astronauts are often asked is why all Apollo landings occurred on the moon's near side. The answer is straightforward. As Charlie Duke explained, maintaining direct communication with Earth was critical. If an emergency occurred on the surface, astronauts needed immediate contact with mission control. On the far side, direct radio communication was impossible. Today, relay satellites in lunar orbit could solve this problem, but such infrastructure did not exist during the Apollo era. Interest in the moon's far side is now growing rapidly, particularly in anticipation of future human missions. Scientists have long advocated for placing astronomical observatories on the lunar far side. If positioned within craters, these observatories could also be protected from solar radiation, making them uniquely powerful tools for astronomy. Shielded from Earth's radio noise and light pollution, far-side radio and optical telescopes could offer unprecedented clarity when observing the distant universe. Despite decades of study, scientists still lack a complete explanation for why the moon's near and far sides look so dramatically different. Renewed lunar exploration is therefore especially exciting for planetary scientists. With NASA preparing missions to the moon's south pole, interest in lunar science is at its highest point in decades. Noah Petro, a project scientist for NASA's Lunar Reconnaissance Orbiter at the Goddard Space Flight Center, emphasizes that the moon's origin remains the most fundamental unanswered question. Understanding how the moon formed and how that process relates to Earth's formation underpins nearly every other aspect of lunar science. Apollo 11 played a crucial role in launching this line of inquiry by returning roughly 50 pounds of lunar rock.
Samples. Analysis of these samples led to the most widely accepted theory of the moon's formation, the giant impact hypothesis. According to this model, a Mars-sized body collided with early Earth, ejecting molten debris into orbit that eventually coalesced into the moon. Chemical similarities between lunar and terrestrial rocks strongly support this idea. However, the theory is not without problems, and scientists still struggle to explain how the moon's initial global magma ocean cooled and evolved into the dry, gray surface we observe today. The discovery of trace amounts of water on the moon roughly a decade ago further complicated the picture, as water is difficult to reconcile with the intense heat expected from a giant impact. Reconstructing the moon's past, much like reconstructing Earth's history, requires extensive geological fieldwork. Apollo rock samples also raised another puzzling question. Why are none of them older than the moon itself? The moon formed over 4.5 billion years ago, only about 60 million years after the solar system's birth, yet most Apollo samples date to around 3.9 billion years ago. This is surprising because the early solar system was far more violent, and older impact-formed rocks should be abundant. To explain this, scientists proposed the Late Heavy Bombardment, also known as the Lunar Cataclysm, a period roughly 3.9 billion years ago when the moon was subjected to an intense barrage of asteroid impacts. One leading idea suggests that the outer planets once orbited closer to the sun and later migrated outward, gravitationally disturbing vast populations of debris and sending them toward the inner solar system. This hypothesis neatly explains the ages of Apollo samples, but it raises an important question. What triggered this sudden spike in impacts? Another hypothesis argues that the apparent clustering of rock ages is misleading, caused by contamination from a single massive impact. The final Apollo missions collected samples from the Imbrium, Serenitatis, and Nectaris basins. Recent studies suggest that material used to date multiple craters may actually originate from the Imbrium impact alone, the largest of them all. If true, this would undermine the evidence for a prolonged bombardment period. Resolving this debate will likely require samples from regions unaffected by Imbrium ejecta, such as the moon's south pole or far side. If new samples from these locations prove significantly older than 3.9 billion years, scientists would gain powerful insight into conditions in the early solar system,
and finally determine whether the moon truly experienced a catastrophic bombardment or if the evidence has been misleading all along. That said, scientists are particularly interested in the moon's south pole as a future landing site for one crucial reason: water. Yes, the moon does contain water, not just trace amounts delivered by interplanetary dust, but significant reserves that were confirmed for the first time by NASA in 2009. Researchers now believe there may be vast deposits of water ice hidden beneath the surface, especially in permanently shadowed regions near the lunar poles. This discovery is a game changer for future lunar exploration, as water ice could be used for life support, drinking water, oxygen production, and even rocket fuel. Despite this excitement, a major question remains unanswered. How did all that water get there? At present, no single explanation is definitive. Paul Hain, a planetary scientist at the University of Colorado Boulder, outlines 3 leading hypotheses for the moon's water origins. The most widely accepted theory suggests that water was delivered by comets and asteroids, vaporizing upon impact and gradually migrating toward the colder polar regions. Another possibility involves the solar wind. Hydrogen ions streaming from the sun may bond with oxygen in the lunar regolith, forming water molecules that later evaporate and migrate. A third hypothesis proposes that water was already present in the moon's original material and was brought to the surface through ancient volcanic activity. It's entirely possible that all 3 processes contributed, raising the question of how much each mechanism played a role. Encouragingly, early evidence supports at least part of this picture. In 2009, NASA launched the Lunar Crater Observation and Sensing Satellite, LCROSS, which intentionally impacted the moon's south pole. The resulting plume revealed not only water ice, but also other elements commonly found in comets, suggesting that at least some of the moon's water originated from spaceborne impacts. To determine the precise contributions of comets, asteroids, and solar wind, scientists will ultimately need to collect samples and analyze their isotopic composition. That is the only reliable way to definitively trace the water's origin. Even if the source of lunar water can be identified, another mystery remains. How did it become so concentrated at the
poles? Hain notes that researchers are divided on whether water vapor from impacts can freely migrate across the moon's surface, or whether it becomes trapped in the regolith before reaching the poles. Only further missions, robotic or human, can resolve this debate. One of the more provocative questions scientists ask is whether extraterrestrial life could exist on the moon. While this has nothing to do with popular little green man conspiracies, some researchers speculate that ancient bacteria could be preserved in subsurface ice. Astrophysicist Professor Christopher Palma of Penn State has suggested that comets may have delivered the basic building blocks of life early in the solar system's history, remnants of which could still exist in lunar ice, until a mission equipped with deep drilling capabilities is sent to the moon. However, this question remains firmly in the realm of speculation. Another intriguing mystery lies beneath the moon's south pole, a massive, unexplained structure hidden below the largest impact crater in the solar system. While its exact nature is unknown, scientists are confident that it significantly affects the moon's gravitational field. The leading hypothesis suggests it is a dense metallic remnant of an ancient asteroid that struck the moon billions of years ago. What puzzles researchers is why this mass remains trapped beneath the surface. Given that the moon's interior is still partially active, heat should have caused such material to migrate. Instead, it remains locked in place, an anomaly that continues to defy explanation. Adding to the moon's complexity is the discovery that it experiences regular earthquakes, known as moonquakes. Seismometers placed during the Apollo missions recorded these events between 1969 and 1977, revealing that the moon is far from a geologically dead world. Some moonquakes are caused by thermal expansion, others by tidal stresses from Earth's gravity, and still others by meteorite impacts. However, several shallow moonquakes appear to occur without a clear trigger, and their behavior remains poorly understood. Scientists argue that a modern global seismic network on the moon would be invaluable for pinpointing the causes, timing, and effects of these events. The data currently available is more than 50 years old and insufficient for definitive conclusions. Researchers also continue to investigate why we only ever see one side of the moon. The moon is tidally locked to Earth, meaning the same hemisphere always faces us. While tidal locking is common among moons in the solar system, scientists still do not fully understand when, how, or under what conditions it occurs. This mystery is closely tied to the moon's formation and early evolution. Understanding tidal locking has implications far beyond the moon. It could help determine whether tidally locked exoplanets, such as those in the TRAPPIST-1 system, might still be capable of supporting life. The moon's surface itself serves as a remarkably well-preserved record of the early solar system. Lacking a thick atmosphere and significant volcanic activity for billions of years, its craters remain largely unchanged. Professor Saxena, a postdoctoral researcher at NASA's Goddard Space Flight Center, likens these craters to pages in a history book, if only we could learn how to read them properly. As discussed earlier, one leading theory proposes that around 3.9 billion years ago, the moon experienced an intense period of impacts known as the Late Heavy Bombardment. If surface samples from unexplored regions confirm this event, it would dramatically reshape our understanding of the solar system's formation. It would suggest that the outer planets once orbited closer to the sun and that Earth itself may have been heavily bombarded, potentially vaporizing any early surface water and erasing nascent life. Ironically, while Earth's early history has been largely erased, the moon has preserved it. Saxena and his colleagues recently concluded that during its first billion years, the sun likely rotated 50% slower than comparable young stars.
by analyzing the moon's unusually low levels of sodium and potassium, despite its otherwise Earth-like composition. The team modeled how solar activity could have stripped or deposited these elements. Their findings suggest that the sun's slower rotation rate explains the moon's current chemistry. This insight also helps explain how Mars and Venus lost their atmospheres and how early solar activity shaped Earth's own atmospheric evolution. As NASA and other space agencies plan for a sustained human presence on the moon, many critical questions remain. In the grand scheme, the moon is not just a destination. It is a stepping stone towards understanding the origin of the solar system and the conditions that made life possible. Solving its mysteries may ultimately help us understand the beginnings of everything we know. That's all the information we have for you today. Share your
Thoughts in the comments below, and thank you for watching. If you're interested, be sure to explore more of our space-related videos.